part of the methods section for Dinesh's paper. Originally, when we had gone over Dinesh's paper, there was some confusion regarding the methodology of the computational part of the study. And so what I decided to do is, for my presentation, since I don't necessarily know a lot about, Lindbladian, sort of methods, that I would go over, some of the very basics of Lindbladian methods, as well as, doing a couple simulations using qubit, which is something that the paper used for their sort of mechanistic part. And so I would just like to go over sort of the basics of Lindbladian methods, as well as showing some of the work that I put in for, that sort of like coding section, as well as some graphs for very basic situations, such as like a one.
This Miss Stephanie treat all her friends like shit. She needs to get second light bulb and therapy.
Levi.
Oh no.
You're not mute.
Oh, my bad. I'm sorry.
All right.
Can I ask a question? So
yes.
This method, you like what kind of sources did you use for getting insights into this method? Because I don't think that it was really reproduced either in the paper nor in the supporting information, right?
Yes. And so most of the ways that I learned through, or learned about the Lindbladian sort of like, or Lindbladian methods is through a documentation on the qubit website, which has been very helpful. Essentially it talks through sort of the derivation of the Lindbladian, as well as, how to actually use Lindbladian methods for unitary and non-unitary evolution, as well as a couple of scattered like PDFs, and also the textbook that Dimitri gave me from Paul R. Burnham, this one right here, if you can see it. It's a little bit tough to see. But yeah, so I read through this as well. And it went over it very briefly. So that's most of the gist, as well as, talking with Braden, who has a bit more knowledge than I do on the topic. But we plan on possibly using this for future projects, just, again, as sort of like a tool in the tool belt. So yeah. Good question. Let me check chat here real quick. Okay.
That'll be good. You can go further.
Okay, yeah. So I just want to start out with the von Neumann equation and sort of the derivation of getting to the Lindblad equation. So first things first, von Neumann equation. And so I'm pretty sure most people in the call know about the von Neumann equation. I'm assuming this is mostly going to be a review. The von Neumann equation is basically just an extension of the time-dependent Schrodinger equation, but instead of using wave function mechanics, it uses density matrix mechanics. And so using density matrix kind of has an advantage over wave function methods, just because of the fact that density matrix can sort of show systems that wave function equations sort of can't. And so just in general, it's a bit more general than wave functions. Yes?
Since we start talking about it, right now you just said, like, I'm just rephrasing what you said. You said like we use using the density matrix approach is better because it is better.
Yeah, to some degree. I'm more or less saying that the density matrix approach is more general than wave function approaches.
But what, again, it's the same as saying better because it is better, or accurate because it's more accurate. So what exactly the density matrix has, which is not really kind of representable maybe in the wave function approach? In
wave function approach, right. So,
and I think this method is in particular is very important when we go with the time-dependent cases.
Yes.
When it's the evolution of something.
Right, yeah. And so,
and this feature is dealing with, no, I'm out of my hints actually. I just give this right name, coherence.
Yes, coherence, yeah. And so essentially,
in explanation now.
Right, yeah. So I'll go into that explanation a little bit. So when we're talking about the density matrix, we have sort of two elements. So we have the diagonal elements and off-diagonal elements to its sort of like matrix. And so when we talk about the diagonal elements, it's essentially talking about the population of each state. Whereas the off-diagonal elements talk about the coherence between states. And so like, if states are coupled, et cetera. And so the reason why density matrix approach is a little bit more general than wave function approaches is just due to the fact that you have that sort of like coherence notion inside of the density matrix's definition, as opposed to just straight up, the values, the state values.
And Dmitry, can you contribute to this definition? Maybe
I can contribute to the process of torturing August.
Good. Yes. well, this is a good thing. I've got to learn. So.
Okay, I'm happy to hear that you are positive about it. So, if we take quantum mechanics as it is typically taught and consider an excited state, how long would its system would stay in the excited state? If the excited state is an eigenstate of the system.
Excited state is eigenstate of the system. Yeah. I'm not 100% sure. I would probably say it depends on the stability of that excited state, as well as the
like postulates of quantum mechanics. The system prepared in one of its eigenstates.
I'm sorry?
There are postulates of quantum mechanics. If the system is prepared in one of its eigenstates,
okay, yes.
will it change its state or stay there forever?
Mm-hmm.
Yes or no?
yes.
I would agree, yes.
Yes. Okay. And if we try to project this postulate to the real life,
yes.
So if you have a molecule or whatever quantum dot or any object that you excite into excited state,
yes,
which is an eigenstate, will it stay there forever?
Not necessarily, I don't think.
Okay.
No.
It has some certain lifetime.
Yeah.
So we are coming to the stage that regular quantum mechanics fails to explain lifetimes.
Mm-hmm.
And the object that you are offering, density matrix, is intentionally designed to describe lifetimes.
Yes.
So can you add more words in which situations lifetime comes into the game? What is the keyword?
Coherence.
Nice seeing you. Not only coherence, something else.
Something else. Okay.
And in the paper that we discussed whatever months ago, this was included.
This was included. Okay. Yes.
Okay, I see it is a real torture. So let's speed it up.
Real torture.
So the keyword is isolated. So isolated system will stay in its eigenstate forever, but nothing in the real world is isolated.
Is isolated completely. Yes.
So everything is interfacing solvent, substrate, and some other. So in case there is a heat bath, which is a concept to take into account everything except our primary system, then this density operator helps to speak about finite lifetimes.
Yes. Okay.
So you were 50% correct, telling that density matrix is needed to describe coherency, and second half that it needs to describe open systems with a finite lifetimes.
Ah. Okay. Yeah.
Yeah.
Thank you. I appreciate the addition. Yes. It's very, very helpful. I appreciate it. Okay. Yes. So yeah, so just generally that's the reason why the density matrix is a little bit more general than wave function mechanics, just due to the fact that again, restating what Dr. Kaelan had stated, not only just the coherence cases but also lifetime cases where we don't necessarily have a definite isolated system, where we have an open system or a more open system. Oops, I clicked on screen. All right, there we go. And so to get to the Lindbladmaster equation, it's a little bit more involved than usual, but I have to sort of skip over a step just to make this short. So first thing, you start off with the von Neumann equation, and since your state vectors evolve unitarily via system Hamiltonian, you can describe the rho dot via, or the time evolution of rho via the evolution equation, or at least the conjugate times the rho times, the regular evolution equation or evolution operator. This is due to the density matrix satisfying the evolution equation, just simply. And so from there, we can do a system extension. So let's assume that our measured system S is like some subsystem of another system. And so this would make it so that if our Hamiltonian is just in system S, it would be non-unitary due to the fact that it wouldn't conserve population necessarily. So from there, the pure density matrix for the joint system is given by R in the equation here, where phi and chi are our orthonormal bases for S and S prime respectively, as well as a normalizing factor on C. Oh, yes.
So can you tell a little bit more in a human language for easier digestion of what is S and S prime?
S and S prime. So S is just a subsystem of S prime. So essentially we're assuming that S is some sort of system inside of like a bath, we could say, where S prime is sort of the bath. So S is our individual system and S prime is our sort of like environment that our subsystem is in.
So you're explicitly speaking about open system, which will have finite lifetimes.
Yes, correct.
Okay, yeah, thank you.
Yes, no problem, yes. And so the math here is a little bit, again, it's a little bit tough to understand because of all, sometimes the symbology can be a little tough to understand. But the basic gist is that all we're doing is we are just extending the system to, instead of just a single isolated system, to a system inside of some sort of extended system. And so that's all we're doing to our density matrix here. From there,
have one question.
Oh, yes, Dinesh.
Yeah, in the previous slide, so rho as a function of t equal to rho0, and your power minus ist and another multiplied with e power ist, does it simply give 1? Finally, it became like rho of t equal to rho of 0 from your equation.
Yes, it depends on if H is unitary. So if it's unitary, then it should just give the answer of rho0 at 0. Since, oh, sorry. Sorry, Dr. Kim.
So what is H?
H is our Hamiltonian.
Is it number, matrix, or operator?
It's an operator.
So it would modify. And what is rho? Is it a number, matrix, or operator?
Rho is a matrix.
Or operator if we do not specify cases.
Yes. Mm-hmm.
So we have basically 3 matrices.
Yes.
Not matrices, matrices.
Yeah.
And they affect each other, and they would not be swappable. So definitely something would happen. The question that Dinesh has asked would be, his hypothetical answer would be correct if rho and H are numbers. But since they are matrices, rho of T will be substantially modified.
Yes.
So sorry for interfering. I just
No, absolutely. I appreciate the answer. I appreciate it. Yes. And so, yeah, like Dr. Killen said, it would be modified, especially since, E to the minus I HT is like sort of this super operator. So it's not necessarily like a number or some like definite value. It's an operator of an operator, which already the operator, well, yeah. So essentially we have, multiple matrices here. So yeah, sorry for the confusion. Does that answer your question, Dinesh?
Yes, so you mean density matrix at time t is always equal to density matrix at time 0?
Not necessarily. What we're saying is that the evolution is defined by this sort of like super operator that we put in. So it just means that initial part at time 0, that just gives us our population at time 0. And then we can evolve using those super operators that we've added on, which are those e to the minus iht parts.
Okay.
Okay, yeah. So it's just evolving the population. Yes.
May I add more?
Yes.
So if the density matrix describes a system in the eigenstate and or thermal distribution where off-diagonal elements are 0, whereas there are no coherences, then it may stay unchanged over time. So there are situations when hypothetical answer of Dinesh are correct, but
yes.
it is a very limited set of quantum states when evolution is doesn't change density matrix. So if it is eigenstate or thermal state where there are no off-diagonal elements.
Yes.
In a way, how is it written already in this 1, 2, 3, the set bullet on the left? It is like you can read that the evolution operator exponent minus iht acting on the density matrix at the initial moment of time at time equals 0, right? But when it is acting, when the evolution operating acting at some moment of time at some other operator, of course it changes the operator. So it's just another way to say how the density matrix depends on time. You either say that matrix depends on time, or you just rewrite like function which depends on time at some way, or you write it like evolutionary operator acting on the initial density matrix, which is pretty much the same as it is changed, and then it's changed at each moment of time according to this operator.
Yep.
So having this density at 0 in this equation, of course, doesn't imply that it's staying like this forever. It doesn't imply that density matrix is not changing, because you have a evolution operator in front, which is changing this density according to the according to the time moment when it is acting on it.
Mm-hmm.
Yes.
So the third bullet shows two things: differential equation where dot stands for derivative, and solution of this differential equation. It's just a comment that may make someone more happy.
Yeah.
Yeah, also, you forgot to divide by h cot in e power ist divided by h cot, means the reduced Planck's constant.
Oh, yes. I'm doing this in natural units. And so the von Neumann equation technically has negative I over h bar as its like sort of a, non-natural unit analog. But right now I'm using natural units. And so basically these sort of constants just, don't really matter. Yeah, that's a very good observation. Thank you. Yes.
Okay. What does this like a summation IM mod CIM square 1 represent actually?
Yeah. So basically what this is a density matrix with 2 individual bases. So our 2 individual bases, which are orthonormal to each other, are from S and S prime, where S's are the phi I, and S primes are the chi, like sort of M chi, N. And so essentially what it's doing is it's the same exact equation as we had with the, let me see here if I have it up here.
Yeah, actually, I want to say that this term actually represents the probability, Probability. This in your previous slide.
Oh, yes.
Yeah, this summation IM mod CIM square is actually the probability for the orthonormal condition. This represents the probability, as I know.
Partially, yeah. So more or less what it is you remember like from this slide here what the density matrix shows, right? So we have like rho is equal to ket of phi, bra of phi. Where essentially we're forming this sort of like matrix where the diagonal terms are definitely your probabilities of individual states, but your off diagonal terms are your coherences of those states. And so that phi term isn't necessarily 100% probability. You're missing a portion of it. And so it's the same thing with this. It's just that instead of using one basis, like we're using originally with that sort of like initial case of density matrix, we're using two bases where one is defined in S and one is defined in S prime. So again, we're just defining this phi part, or we're defining this, density matrix, just with two bases instead of one. Does that sort of make sense?
Yeah. Okay.
Yeah. Yeah. So that's what that summation sort of describes. And then also that bottom part is just for normalization purposes.
Thank you.
No problem. Yes. Thank you for the questions. Yes. So the next part in this is to take the trace of that pure density matrix that we originally had with respect to the S prime basis. And so from here, all we end up with is that diagonal term from that sort of S prime basis. And so this just preserves the probability of that S prime basis. And from there, we just end up with that summation times that CJM, which is that sort of, basis, or the two probabilities for both bases. And so then we end up with 5i ket 5i bra. And this just gets us our sort of, how do I say this, imperfect density matrix, where essentially we have the probabilities of both system 1 and system 2, which if it's the entire environment of our system, it should be equal to 1. The total probability should be equal to 1. However, that's not necessarily 100% the case. But since this is Hermitian, essentially has a trace of 1. And so the probabilities are 1 in this case. We're making them be 1. So then we end up with, yes, just a trace of 1. The density matrix of S and S prime will then be Hermitian, and the density matrix for the subsystem S generally isn't. And so essentially what we're doing is when we're doing this system extension, we're just normalizing it so that the total probability will be 1, as opposed to when we're just looking at subsystem S, we won't have necessarily a unitary density matrix, or a unitary density matrix. And so essentially when we're extending the system, we want to make sure that our probabilities are always 1. So our population is conserved. And from there, we can apply something called absolute positivity. Applying that to the constraints originally in the previous equation nets that what's called the Lindblad equation. And so we have here the non-diagonalized Lindblad equation, and then simplifying for this, we end up, or non-diagonalized, sorry, we just end up with a extended form of the Lindblad equation, and simplifying this, we end up with the more simplified Lindblad equation, which is more often shown in papers, where these sort of brackets are shown to be our anti-commuters, and the L operator is something called the Lindblad jump operator, which I'll discuss in the next slide here.
Oh, maybe it is not defined in the next slide. What is alpha?
Alpha is our indices for dimension.
But what does it count? And why number range of alpha indices goes to n squared? And what is n?
N is supposed to be our dimension. So
Dimension of what?
dimension of matrices, if I remember correctly.
Oh, okay. So as many L operators, as many independent elements in the matrix.
Yes.
In the density matrix of primary system. Okay.
Mm-hmm. Yes. And generally for very, very simple situations in, let's say 2 dimensions, right? So we have 4 minus 1, 3. Essentially, the reason why we have those A's there is because, sorry. Okay, Gotcha. But essentially, the reason why we have those A's there is because those jump operators have a constant in front of them. And so those constants are going to change in between, specific parts of dimension. And so it's a little bit weird, but here, let me go over here. Yes. So essentially, they're just diagonalizing any orthonormal basis. And in order to do that, you need to have certain constants, as well as n squared minus 1 dimensions for them to be proper. So
August,
yes,
are you going to give examples of Lindblad operators or just tell?
yes, it'll be a little bit later, and so that'll be in our single qubit section. So it'll give an example there, and then it'll also show the full form of the equation for that. So that should clarify things a little bit. Okay, understood. So from here, the Lindblad equation. So our L operators are called the Lindblad jump operators. Essentially what they're doing is they diagonalize any form of orthonormal basis that we want. So for instance, we can define them as basically anything we want as long as it's orthonormal and diagonalized. And as long as it describes that the system that we're actually properly describing. So it's the basis for the system. The first part is unitary, which is the von Neumann part, whereas the second part is non-unitary. This is purely convention. This is not necessarily 100% a constraint, but generally when we write down the Lindblad equation, we want the first part to be unitary and we want the second part to be non-unitary. Again, this is just purely convention. This is not necessarily 100% addictive of, every single system. So, all right. So moving on to the computation section. So there are two evolution types that we worry about when we're doing, Lindblad methods of evolution. The first one is unitary evolution, where all operators, Hamiltonian and Lindblad jump operators, are unitary. So the conjugate transpose is the operator's inverse. This preserves normalization and eigenvalues / eigenvectors when operating on an object. So population, essentially what this means is that population is conserved due to properties of a unitary Hamiltonian and the Lindblad jump operator. So normalization does not need to be carried out during computation. So you normalize it once and it's done. You never need to worry about normalization again. Normally, this is for when systems include every part of the system. So that includes the subsystem and the environment. So if we have a full Hamiltonian, then it describes, both the subsystem and the environment, and we end up with unitary evolution. However, most often we have non-unitary evolution, which means that since our entire system and environment, adding both of those together is messy and also a computational mess. So instead we can use non-unitary evolution to propagate a subsystem instead of just the subsystem in the bath. As long as you defined specific constants associated with that bath, then you should end up with the proper time of evolution. And so in this case, the conjugate transpose of any operator is not necessarily the operator's inverse. Normalization is not preserved, and there's no population conservation in the Hamiltonian. So one way of treating this is to, in each time set, to normalize separately. That's not necessarily the only way of, dealing with non-unitary evolution, but it is a very common way of dealing with it. And so from here, we need a couple of approximations. Oh, let's see here. Saw my some chat. Okay, gotcha. So specific approximations that are necessary for computation with Lindblad equation. So first off is the Markov approximation, where the system has quote unquote short-term memory, meaning that the system has no recollection of past events. Essentially, you can assume this as the system having infinite degrees of freedom and infinitely fast energy transfer between specific parts of the system. Another one is separability. Essentially, given a system state at T0, we're assuming that they're factorizable as opposed to entangled or correlated. As such, the total density matrix can be represented as phi total of 0 is equal to phi initial of 0 tensored with phi of the environment at 0. So essentially what we're saying is that there's no real correlation between total and or sorry, the initial system and initial environment density matrices. Another one is the Born approximation. This works if the interaction is weak and if environment is 112. Sorry, text boxes. But essentially, if the environment is much larger than the system itself, essentially the system remains separable throughout the evolution of system states. This is essentially using separability, but for any time t. It's very similar to the Markov approximation. Another one is the secular approximation, which just states that similar to the rotating wave approximation, if terms rotate fast over time integration, they're neglected, whereas this leaves only slower rotating terms over time integration.
August,
Yes,
your bullet point number 3,
yes,
it's time t on the left.
yes.
and
I
time
just realized that. Yeah, it's supposed to be time t. Yes,
for both.
yes, for both.
Thank you.
Apologies. Yeah. So instead of the zeros here, it's supposed to be t. So rho I of t tensored with rho I environment of t. If that makes sense. I apologize. That's on me. Sorry about that. So here, see something. Let me see here. No, not only at the initial time. It's at any time step t if the system remains separable throughout evolution of system states. Essentially, this is only if the interaction is weak, and so if the Born approximations, initial constraints are satisfied, then it's constant throughout the whole evolution. So the approximation holds constant throughout the whole evolution. Initial time is only for separability.
And a question maybe not exactly related to the previous one, but when you talk about Markov how to pronounce approximation,
Yes.
in short-term memory, can we say that in this case, if this approximation is applicable, then coherence should be reduced or decreased in these conditions?
I would say decreased.
Increased?
Decreased.
Okay. I agree, but I'm not 100% sure. Yeah. So
Okay.
like if
Yes.
there is a very short memory on what happens before, it means that we can think about state being more like a isolated pure state, right?
Yes, exactly.
Am I right, Dmitry? What do you say?
No, short memory means there will be damping at each time stage.
Complete.
And, no. There will be memory constant. So differential operator, differential equation will be linear. It will be linear differential equation with constant coefficients. If one violates Markov approximation, then coefficients in the differential equation will be time dependent, or one would need to go from differential to integral equation where this memory will be holded, and like typically in differential equation we write derivative equals some function of the function, some operator acting to the unknown function, and it is linear. Operator is acting on the unknown function in the first power. As soon as we violate Markov, it may go non-linear. It will depend not only on the unknown function in the one infinitesimal time before, but on the whole history, how the function was acting before, and it will make solutions more complicated, and typically instead of damping, it will be some revivals and some additional coherency.
Yeah. So I will rephrase my question. If I know that in my system coherency is very strong, means it's very highly coherent system, then Markov approximation probably should work better in these conditions, or backward.
So there are two things. amount of coherency in the primary system that August called as S. And there is a way how the interaction with bus is treated.
Yeah,
Which
but they are
maybe
connected.
Markov-
Should
which maybe Markov- so
be connected. In other words,
they're not connected. They're not connected. The way how the system interacts with bus is just a model, and amount of coherency is more like initial state.
yes, but in this case, can I choose the approach, whether it is Markov approximation or not, just thinking about coherency of my system?
No, I wouldn't do so, because applicability of Markov approximation does not depend on the primary system. It would depend on the bus. If the bus is very coherent, then yes, Markov approximation will fail.
I see.
And I wanted to ask August, but I better quickly comment myself another 5 seconds. Examples, or August, if you can quickly answer, what are typical examples of the environment of the bus in the examples in the situation when you describe and generally?
I don't know. Yeah. So, goodness.
Okay, if it doesn't come up quickly, we'll see. Maybe you will have it in your slides. But one of the examples, which is not the only one, often one can consider primary system as set of electronic degrees of freedom levels, and secondary bus the nuclear degrees of freedom oscillations.
Okay.
It's one of the examples, but there are much more possibilities. Okay.
Okay.
I'm
Yes.
done. Yeah.
Thank you. Appreciate it. Yes. Okay. Here's the part where I get into sort of more the computational setup that I had done, just based off of some of Braden's calculations, as well as some of the tutorials on Qubit. So the first one was using a Hamiltonian of 0. So no Hamiltonian to speak of whatsoever. The Lindblad jump operators as our polyspin matrix Z. So this Z polyspin matrix. And our initial density matrix of 1.5, 0.50. So we have a entirely a probability in the initial state of 1 for state 0 and 0 for state 1, and then coherency between the both as 0.5 on the off diagonal. Then from there, we define our Lindblad equation, and then as well as our damping term. And from there, you end up with a matrix that defines the time evolution of these states, which is shown on the bottom here. So we have the initial state staying at 1, but our coherency goes or decays for both states down to the first state. So our coherency goes down to completely 1, but our probability stays in state 0. L0 is our jump operator. So yeah, physical meaning it's essentially our basis, correct, for both the system and or the subsystem as well as the bath, correct? Yeah, polyspin matrix, yeah. Oh, sorry, yes. Okay, yes. So essentially our basis, yeah, okay. So our states are the spins, Z spins, yes.
Let me add to the discussion.
Dr. Killen, you muted.
Formal answers are correct, but they could be not helpful to learn new things. So Braden is asking not the functional form of the Lindblad jump operator, but physical meaning. Like, why do you have here it's proportional to 1? When it will be like 10 times smaller, 10 times bigger? Which mechanism is behind this jump operator? So how to, in realistic system, where to get the things that you did model by this value 1?
Right, yes.
And the very quick, so quick that partially not correct answer is it is Fermi-Golden rule. So it is operator of interaction between systems S and S prime, absolute value squared multiplied by density of the state of system S. So it is a rate of transitions between eigenstates in system S, which is a square of the interaction between system S and S1.
Okay.
Braden, would you be more happy with this answer to your question?
Sure. Yeah, that was even too much, but yeah.
Thank you.
Okay.
I was just going for the fact of the decoherence effect only in this type of diagonal jump operator.
Okay.
It looks like August did select the very simple example with everything which is possible set to 0 to make it solvable. I think it is not numeric, but analytical, mathematical, or equivalent program. So to make an example on one accessible in one page.
Yes. Yes. And so, yeah, that's the basic gist of this system. Yeah, very simple. So for the next system, it's a very similar set of equations. For our L naught, though, we are using the poly X spin matrix, as well as, pretty sure everything else is pretty much the same. Let's see here. Yes, so everything else is the same, but instead of using the Z polyspin matrix, we're using the X polyspin matrix. And from here, what we see, at least, is instead of decoherence, we see extreme coherence, where we end up with a superposition of states over time. So instead of just purely seeing one state, we see, you know, sort of this superposition of states. So we end up with better coherency than in the previous example. So extreme coherency instead of extreme decoherence. Oh, Dr. Gunn, did you have a comment to make? Sorry.
No, I'm just smiling and I'm expecting that someone will ask the questions.
Yeah, okay. I was checking to see if anybody else had questions. Okay, understood. Yes. Okay. Does anybody need more time to look over this slide? No? Okay, gotcha. Sounds good. All right, so from here, we start getting into qubit, which is a computational extension to Python. And so from here, we can define, let's say, oh,
August,
yes.
Then if you're going to next chapter, I'll give a quick comment on the previous one.
Okay, yes.
The examples on the last two slides are where L with superscript alpha was selected with different values of alpha, but those are abstract models. In the realistic situations, the relaxation is happening through several channels, and both depopulation and decoherence occur simultaneously.
Yes.
So here, August voluntarily or involuntarily dissected and separately considered mechanism of depopulation and decoherence while in real life they happen simultaneously.
Yes. Mhm.
Done.
Very, very good point. Thank you. Thank you, Dr. Killen. I appreciate that. Yes. Okay. Oh.
Since we have a second presentation, and I think we have a presenter already here, right? Or no?
Yes, I'm here.
Okay, perfect. So I'm
Okay.
just to ask Stephen, sorry, Stephen, August, how many slides do you still have?
Not much. These are the last slides, so last 4. Yeah. And so if you want, I can just show the animations and the sort of graphs, but these are different systems. This is a single qubit state dynamics. So
Introduce and then maybe go to the
Yeah.
give some flavor of what exactly is called qubit, and then you can go with a simulation.
Right. Yes. Okay. Understood. So essentially here we're using a different Hamiltonian, that of the single qubit state dynamics. And so the language can be a little bit hard to parse, but essentially in qubit, you have different types of matrices. So you can either make one, or they have specifically defined ones like the sigma Z, sigma X, sort of matrices, sigma Y. And those are the polyspin matrices. Sigma M, which took me a while to figure out, but that is our destruction operator. And then there's also a creation operator, which is designated sigma P. From there, though, we can define our constants of the system. So epsilon, we're taking B0, delta, we're equaling 1. So we purely have our H in sigma X. And then we're taking our 2 constants, which are associated with our Lindblad jump operators to be 0.5 and 0. So essentially, these 2 are going to define our system decay. And shown in the Analytica solutions here, we see that the decay is entirely in terms of G2. And from the graph, we can see that it decays over time, as well as our phasing between the Y and Z orbitals, or Z orbital states, as being directly pi/2 apart.
So again, what's the difference between blue and green lines? It's just different initial conditions, or what is it?
No, they are our states in SY and SC basis.
Will you show the 3-dimensional where SX and SY rotate on the equatorial?
Absolutely. So this is a block sphere, and you can actually create this in a qubit. And so this will give you the sort of like changing block sphere vector.
This visualization seems to be different from your plot on the previous slide. In previous slide, your SZ is 1/2, and SX and SY are.
Oh, yes, here.
So this would correspond to motion in the equatorial plane.
Right, yes.
Approaching the center.
And so
probably you doing simulation and visualization in 2 different runs.
Yes, correct. And so the visualization here, the axes are not necessarily 100% accurate besides the 1 and 0 state. And so, yes.
What you're showing is a solution when the cavity is activated, when it is continuous irradiation.
Yes.
So it not it experiencing the Rabi flips between ground and excited.
Yes, correct. Yes. And so yeah, just generally qubit is nice for showing these sort of interactions, or these sort of like basic or even like more advanced systems, just because the fact that the actual visualization encoded into the software is very nice. Particularly, this wasn't too hard to create. So showing visualizations and graphs might be a little bit easier using these sorts of methods, as well as using qubit. Oh, yes. Okay. So onto the next system here quickly. All right. So the next system, instead, we use zero damping. So our gamma 1 and gamma 2 are defined as 0. So originally in the second screenshot here, we had, I think it was 0.5 in the previous one. 0.15, yes. So the second value here, instead of it being 0, it was 0.15. But in this case, we're setting all total damping to 0. So since we don't have really any interaction between bath and subsystem, we end up with it all being just frequency in the system. And so from here, when we look at the graph, we see no damping terms or anything like that. It's just purely sinusoidal pattern. And from there, if we look at the block sphere created, we see just this purely, oscillatory pattern between states. Okay. Does anybody have any questions pertaining to this system particular?
This visualization is also provided by this software, QTP software.
Yep. So all the visualization, all the graphs and everything like that are entirely generated within the software.
Nice, beautiful.
Yes, absolutely. And so this is part of the reason why we wanted to check in with Qubit, because the visualization seems to be pretty nice. Currently, since I'm short on time, I will not talk about the correlation functionals, but those were also dissected in software as well, which is shown in Dinesh's paper that we originally started dissecting 2 weeks ago. And so, although I don't have time to do that right now, possibly in a future presentation.
Perfect.
Okay, gotcha.
Thank you. Yeah,
Alrighty.
so thank you, August. And we had a lot of questions on the way. So if we have time, we can return maybe several questions were missed in the chat. So
Yes.
then we can do it at the very end, but we probably need to move to the second presentation. Would you
Okay.
please stop your stop sharing the screen?